Good afternoon, everybody. I am Christophe JURCZAK, so president of Le Lab Quantique. And together with Robert, we're going to present to you, introduce you fantastic speakers for this first webinar of year 21. Happy New Year to everybody. It's too late, but still, it's a pleasure to say that. So it's going to be most probably certainly a very interesting year for quantum in Europe and all over the world. So I remind you who we are. So we're a Paris-based not-for-profit that's running a range of initiatives in support of the quantum ecosystem. Started with meetups when it was possible, high-profile conferences. We're doing webinars since last year, very successful so far, hackathons and other types of conferences. And we're expanding to include other types of activities, and I'll come back to that a little bit later. You've seen most certainly some news from France recently, and we've been involved with some of these initiatives. Very big news last month is that French President Macron unveiled the French strategy, the strategy for quantum technologies, 1.8 billion, out of which about 1 billion, sorry, from the country's budget, dedicated to quantum technologies over the next 5 years, which is substantial and very welcome. We'll be involved, I assume, in some ways in the ecosystem work going on. We've associated ourselves to startups Candela and Pascal to open south of Paris in Massy, a facility called Campus. It's the first quantum co-working space, probably worldwide, hosting startups, and we'll have there's some space available. If some of you, any of you, is interested in opening in France, please reach out to us. It's a very interesting space. There's some hot desks. There's space eventually also for showrooms, conferences. So it's very close to Paris, easy to reach. And we'll communicate more about this over the next weeks. We're very proud also of an activity we had in November, December. So we've worked with Paris region, Région Île-de-France, and GENSI, an institution in France in charge of high performance computing. And we built together a scheme to support or foster the emergence of proof of concept projects associating industry. On the supply side, so quantum computing, hardware, software, and also your brand customers. For example, Pascal has collaborated with EDF on a project that's funded by this PAC Quantique, as it is called. QCware and Total being funded a second project, and third is startup Qubit Pharmaceuticals. Interesting projects. There's some information about that on our website. And there'll be more of these projects over the years. It's really the idea that we need more proof of concept, more collaboration between actors and value chain to create to create traction for quantum technologies and quantum computing in particular. Last, we have a job board on the website. Have a look at it. And two jobs have been posted today or yesterday by Candela. Massy-based startup, and there are some others as well. If you're interested to post, reach out to me, and we'll make sure it's there and available, and we'll communicate about that. Some information about what will happen now. So we'll have the webinar. It's recorded. You will have the link to the webinar within a few days. Actually, it's on YouTube now, so you should find it on the website, through the website and on YouTube pretty fast. And we'll communicate also the slides that will be presented. Today, it's our pleasure to have three leaders and champions of quantum in Europe, very well known in the community. We'll start with Xavier AUBRY from Zaz Ventures, and then Benno and Vincent from startup Qu&Co, based in the Netherlands. We'll talk about their technology. Some rules for the webinar. Attendees can't broadcast their videos. What does that mean? I'm not sure about this one, but attendees are muted, as you've seen. If you want to ask questions, please do it through the Q&A box. And Robert and me will moderate and take the questions and try to to ask them the speakers to make it a little bit more lively. If there are some questions that are not answered during the call, we'll try to have that done in written, yeah, just before the end, and we'll try to communicate that and post that on the website as well. So without further ado, I'll let Robert introduce Xavier, and let's have our first speaker.
Thank you, Christophe. Yes, so we'll start by talking about innovation funding with Xavier, who's the managing founder of Zaz Ventures. Zaz is a leading consultancy in Europe. They are specialized in innovation funding, and they know the field of quantum research quite well, as they helped Pascal and Qblox and IQM to win the EIC Accelerator grant, which is a highly selective grant because the success rate is less than 1%. And that is quite a unique way of helping companies, as they have a no win, no pay approach. So they really work alongside the companies they are very interested into their success. Xavier, thank you very much for being here today. I will leave you the floor for 20-25 minutes so that we can take some questions. Thanks, Xavier.
Thank you, Robert. Thank you, Christophe. Today, we are going to look at the funding instruments that can be found at the European Commission, which is very timely because, as you're probably all aware, the new program was launched earlier this week officially. Although the court's not open yet, the Horizon Europe program, as it's called, is around 90 billion euros in total over the next 7 years. And it has multiple instruments which are covering different types of technology maturity and setups. So today, I hope to be able to introduce you to some of these with the information we have from the drafts that have been released, keeping in mind that the official document will really come end of March, beginning of April. So things are bound to change maybe a little bit until now. And I'll also quickly reflect on the previous instruments, because Horizon Europe is really an evolution rather than a revolution. And you will be able to see what drove these investments and what it took to get funded, from the examples of quantum companies like IQM, Pascal, and Qblox, which we have supported over the past 2 years. So first of all, why European funding? You've all heard about the grant schemes, but you might not know that the Commission is now able to invest directly through the EIC fund in equity, so they can become a shareholder in startups. And so therefore, there are grant instruments, there are equity instruments, and there are blended instruments covering both. If you look back at deep tech and the impact it has on our daily lives, I think the most exciting example is BioNTech, with German companies started by Turkish entrepreneurs. And really for the first 10 years, the funding came from grants from the Commission. And that was at the time where they were not on anyone's radar screen. They were doing this very difficult research on messenger RNA, which could be applied to immuno-oncology and later on, of course, to vaccine production. And because of that early investment, they were able to drive the technology and therefore the value of the company. So the real investment really came only 10 years later in 2018. And of course, now we all know that names since they are behind one of the first vaccines to be approved. So critical role from the EC, because at that time, if they would have tried to go out for funding, particular private funding, they probably would not have been able to raise money, or at least not on good terms. So they would have been heavily diluted. In this particular scenario, they were able to wait until really 2018, raise a very large Series A, and therefore build up the valuation of the company before they have to start diluting themselves. Now, of course, there is a big race going on. You're all aware of it. The quantum race is on. And well, as in other fields, unfortunately, US, Canada, and China got an early start. But there are a number of companies now in Europe which are really catching up and leading in particular spaces. I think it was very interesting to see the progress that has been made. I'm just picking here two. There are many others, obviously. These are good examples because they have been funded by the Commission recently. 17.5 million euro for IQM, close to 7 million, a bit more than 7 million for Pascal. So there is appetite from the European Commission to support these companies with both grant and equity, which is good news. And in fact, the Commission considers those companies as strategic investments because they want Europe to play a leading role in the second quantum revolution. The good thing, and the reason why it's so high on the agenda of the Commission, is that quantum technologies also match the societal agenda of the Commission, which is focusing on impact and in particular societal impact. So if you think about the impact on the world we can have through quantum computing, whereas it's with whether it's with chemistry, material science, or drug discovery, they can be massive impacts, which will come in the coming years as the commercial application come. We know that by modelizing molecules, we might be able to find more efficient carbon capture catalysts. We know that we can use material science to improve, for example, solar panels. We know that the next pandemic will probably be fought with quantum computers. So this is really where the Commission wants to play. And in fact, it's interesting to see that in the Horizon Europe work program, quantum computing is in a sub-program called emerging digital technologies, focusing on the Green Deal, which means environmental impact. And that, of course, is obvious because quantum computing is extremely energy efficient compared to regular supercomputers. So it's actually a way to improve the computing capabilities while decreasing carbon footprint of this infrastructure. So here, the challenge for the Commission is to fund deep tech. And that's really important to understand, in particular in programs like the EIC Accelerator. If you go with a technology which is just incremental improvement or doesn't really have a product market fit risk, it will be more difficult to get funded. So here the Commission is really ready to fund risky innovation that combines both the R&D risk and the product market risk, which is exactly the case with quantum technologies, obviously. There are many instruments, and it's very easy to get overloaded when you look at the program. Lots of what we call Brussels English going on, and a lot of different terms and buzzwords that are not necessarily understandable by everyone. But to simplify, there are 3 pillars which will support Horizon Europe. The first one is really focusing on individual researchers. So if you are in a university, you can apply for grants like the ERC grants. That's the Excellent Science pillar, number 1. But the ones that are really interesting for us to discuss today is the pillar 2 and the pillar 3. Pillar 2 is about the collaborative projects where the Commission is releasing a list of calls and asking consortiums to assemble and position themselves to address those particular topics. And they can cover multiple areas. And obviously, quantum will be in the cluster 4, which is called Digital, Industry, and Space. In this pillar, we're talking about relatively large consortia. There could be small instruments with a consortium between 5 and 10 partners, but in general, the consortia will contain anywhere between 15 and 30 partners. And therefore, the time needed for the proposal will also be longer. We generally recommend to start at least 6 months before the deadline. Then there is the third pillar, Innovative Europe, which is composed of different steps, but the most important one, which represents about 10 billion euros, is the European Innovation Council. And that pillar contains different instruments. We probably have heard about the EIC Accelerator, which is related to the equity funding I described earlier. But there are also other instruments called EIC Pathfinder and EIC Transition, which we will discuss. So in those calls, you generally go either as a single entity, for example, in the EIC Accelerator, it's only for one company to apply, or as a mini consortium in the case of Pathfinder or Transition. And because it's a smaller group of entities, you can apply or prepare the proposal in about 3 months. So let's look at the collaborative projects first. There are different types of instruments. In fact, there are many more than 3, but I start with the main 3 instruments you will see in the work program. They are called Innovation Actions, Research and Innovation Actions, and Coordination Support Actions. These are simply 3 different types of activities. The Innovation Actions are focusing on close-to-market technologies. In EU lingo, we're talking about TRL, technology readiness level, which is inspired from NASA. So TRL 9 is the highest TRL when you're in market, and therefore innovation actions are typically TRL 5 to 8. They will require a fairly large consortium because the grants are between 5 and 20 million. And the funding rate in this case is 70% of the cost. Then there are research innovation actions which are lower TRL, further from market, can be also smaller consortia, and also typically smaller grant amounts, typically between 2 and 10 million, but with a 100% funding rate. And finally, there are coordination support actions which can cover things like standardization, dissemination, communication activities around a specific domain. These are very small grants, 1 to 3 million euro, 100% funded, but they typically have a small consortium because there's not a lot of money for each project. So these are the 3 key instruments you will see in the work program. There are other instruments more exotic, like public procurement, like framework partnership agreement, etc. But these 3 represent really 80 to 90% of the calls that you will see in a work program. So take the example of quantum. The first batch of proposals of calls will be published in April with the final draft, or actually the official program. And in the current draft, we can see a number of quantum-related calls. You can see a few of them. There's one IA around quantum sensing technology, and there are multiple RIAs which cover different aspects of quantum. You can see here quantum sensing, emerging quantum technologies, basic science for quantum, and quantum software ecosystem. Each of the calls has a detailed description. Again, currently only in draft form. You can see here the example of the digital emerging call, which is focusing on promising quantum technologies. And the call specifically even talks about examples like photonic qubits and neutral atom qubits. But what's important to understand once you've read that is to really see how much budget there is. Because, for example, in that particular topic, there is only one project that will be funded at €5 million. And it's very likely there will be many applicants. So maybe this is not such a great topic to address if there is expected high competition. But there are others which may have better chances. So these are things to consider when you're looking at a topic, to understand how many projects will be funded, what is the average funding required, which will directly drive the size of the consortium. If it's a €5 million project, typically you'll have about 10 partners, 8 to 12 partners in the consortium, for example, which will split the amount of funding between themselves. The evaluation process is always done by third-party experts. So it's not the commission employees, civil servants who are evaluating the proposal. It's actually third-party experts like you and me. Christophe, for example, could be on the jury. I don't know if he is, but he definitely has the skills to be. And of course, as long as he's not in conflict of interest because he has proposals in the same call, he would be allowed to judge these proposals. And therefore, if you are interested, I encourage you to register to the database of experts that can be called to be an evaluator. And I'm happy to provide that information offline on how to become an expert or how to apply for being an expert. So as a consortium, you build an application which will be between 10 and 45 pages, depending on the model. And then this application will be judged by 3 to 5 experts who will make the decision as a consensus if that proposal should be funded or not. The timeline is quite long because those people have to typically meet. Of course, with COVID, they meet remotely, but they still have to talk to each other about the application. So there are 2 main ways of evaluating applications. There are 2-stage calls where you first write a small 10-page application, and then you get a selection. Some are kicked out, some stay in and write a longer stage 2 application, which then is evaluated for funding. Total process is about 8 months before you get the notification of success, because then you also need to talk to prepare the grant agreement. That takes an additional 4 months. There is also a scheme which is actually most widespread, where there's only one stage. So here you file directly the 45-page application, and within 5 months you'll get the result if you have been funded or not. That is the standard process for gravity projects. But there are new instruments, in particular with the so-called EIC. The EIC was piloted under Horizon 2020 starting in October, and now it's become a very important instrument because, as I mentioned, 10 billion euros are earmarked for this instrument out of the total 90 billion euro, 85 to 90 billion euro of the program. So the different instruments correspond to different maturity level for the technology. On the bottom, you have the EIC Pathfinder, which is focusing on far-to-market technology, TRL 1 to 4. Requirement is that you need at least 3 legal entities from 3 different member states to be able to apply. And the grant is capped at 3 million euro with 100% funding rate. Then above that, you have the so-called EIC Transition, which is focusing on TRL 4 to 6. We're talking really about prototyping the technology at this stage, demonstrating the technology. And here you can apply either as a single applicant, typically a company. It's very unlikely it would be a research center, or a group of entities. It could be a company supported by research and academic partners, for example. Maximum grant 2.5 million euro, 100% funding rate. And finally, there is the holy grail of EU funding, which is called the EIC Accelerator. Here we're talking about late stage, TRL 6 to 8, or even TRL 9, because you are allowed to launch a product on the market and get money from the Commission in the form of equity to fund that market launch. You can only apply as a single applicant, no consortium allowed. But here you can go for large amounts, 2.5 million euro of grant at 70% funding rate, only for one company, and up to 15 million euro of equity. Now, of course, because it's such an interesting instrument, it's been extremely competitive, less than 1% success rate in October, which was the most recent cutoff. The focus of the EIC Accelerator is clear. It is deep tech innovation, market creating, which will have a long-lasting effect on job creation and also societal impact. So if you tick all those boxes, you should be considering that instrument. But you need to be a for-profit company. You need to have some traction. So typically we recommend to apply once you've reached a team of 8 to 10 people at least. You've raised some seed funding of about 1 million already. You have a technology prototype, and then you're going to use that money to essentially fund your A or B round. This is really the sweet spot for the EIC Accelerator. The eligibility is actually that you need to have reached this TRL 5 or 6, which means prototype. And the grant component will allow you to develop that further up to TRL 8. Then you can also apply for equity, which will fund other things. Actually, the equity in theory can fund anything, but it's usually used for TRL 8 or above. I think for quantum computing, because there is so much research to be done, it's not uncommon that the companies will use the equity to fund lower TRL activities. So you can spend, if you want, 10 million on TRL 6 or 7 activities, including grant plus equity. The way the funding is distributed is that first you sign up the grant and you receive about a bit more than 50% of the grant upfront. So if you've asked for 2.5 million euro, you get a nice check of 1.25 million euro on your bank account, a bit more actually, when the project starts. And then you receive the rest of the funding in the 2 years that typically the project lasts. In parallel, the Commission starts an equity negotiation process with you, and they will organize it in tranches. It can be 2 or more tranches, depending on the size. In general, what we've seen for average type of funding is 50% upfront as convertible debt. Upfront meaning once they've done all the due diligence, so that's probably 12 months into the project. And then the remaining 50% as an equity inside the round in the second year of the project. There's about 600 million euro of money allocated to open calls and 500 million focusing on challenge-driven calls, which include quantum computing. So quantum computing is specifically identified as one of the important challenges in 2021. The process required 2 steps, short and long application. We'll see it a bit later, but the deadlines are for the short application, no deadline. It's a rolling basis, so it will start already in March. For the long applications, you have 2 deadlines to keep in mind, 9th of June, 6th of October. You do need to first go through the short application before you're allowed to go to the long application. The success rate have been very low historically and dropping rapidly because there were more and more submissions. You can see here going from 4% when they introduced the scheme up to lower than 1%. 4,223 companies submitting in October, only 38 funded. But the new process that they put together for us in Europe will aim to reduce that oversubscription. So here they have a 3-stage process. First, the short application described, which includes a 3-minute video pitch, a normal pitch deck, and a 5-page form. This is judged. Within 4 weeks, you get the answer, go or no go. If it's a no go, you get a second chance to submit. If it's a go, you go to the full application stage, which should be around 20 pages. Within 5 to 6 weeks, you get invited or not to interviews. If not, you have a chance to file again at the full application. If you are at the interview, you'll be facing a jury of 6 external jury members, which come from the business world, typically business angels, venture capital firms, incubators, which will then give you a go or no go. If it's a no go, they might send you back to interview or send you back to the full application stage. If it's a go, then you'll get the money with 2 parallel process. First, the grant agreement, and then in parallel, the equity negotiations. If you fail twice, you'll be kicked out of the program for at least 12 months. There's a cooling off period. So these new steps will make sure that the subscription should be lower than before, because the problem with the previous scheme was that there was no limit in terms of number of resubmissions. So there was the snowball effect, people filing and refiling, etc. So you can imagine what it was doing to the numbers. Now this is going to be hopefully better. They estimate that they will receive about 10,000 applications in 2021, of which they will screen 3,000 to stage 2, of which they will get about 900 in interviews, and in the end fund probably around 250. These are the forecasts from the commission. We're not sure yet how it's going to play out, but their plan is to get 10,000 applications, to fund 250 applications, which is 2.5% success rate. A few examples to finish. IQM funded in the March 2019 deadline. Interesting thing about them was the very narrow window of opportunity, because they had raised 11 million euro in the previous summer, 2018. So they were already well funded, but of course, with what they want to do, they needed a lot more money. And we knew that they would be raising a fairly large round. So we couldn't wait until they would raise the round, or there would not be any more in scope for the EIC accelerator. So luckily, they got approved at the second submission. We did one in January, one in March. And they got the maximum amount, because for them, it made sense to go for the large amount. Now, of course, you probably have seen that in the meantime, now they've raised a new round of 43 million euro, of which the 15 million euro of equity will be part of. So really interesting company, and one of the flagship here for Quantum in terms of EIC funding. Pascal was funded on the October deadline, the most competitive of all. And of course, very interesting here because they are only starting with early revenues, but they have early adopters. They have partnerships with EDF in terms of industrial application, with Cineca in terms of HPC. They have also ecosystem partners. And at the time, they had just released their article, scientific article about the 100 qubit QPU. So they went to interview and did a great job, resulting into a bit more than 7 million euro from the commission. Same for Q-Blocks. Q-Blocks submitted in October was also as for Pascal, it was their first and only submission, and they got in on the first attempt, got invited to interview. Interestingly, here they already had revenues from the sales of their first control stack hardware, and the commission money was earmarked to scale up their hardware to develop a supercluster unit. They went for a smaller amount of funding, and they ended up with 4.8 million euro of funding. So what is a good application? You have to remember that it's very difficult to get funded, and therefore you have to be excellent. Until now, the scoring system was based on a scale of 0 to 15, but most of the applicants ended up between 13 and 15. So the only way to get invited to interview was to score more than 14.1 at the previous deadline. You can see here the evaluation from Qblocks, they scored 14.4, therefore got invited to interview. What makes a good application into a fantastic application? Of course, there is the intrinsic properties of the case, the technology, the market, the team, but that's not enough. Beyond that, you need to have a very good storyline, very exciting to read, especially for evaluators who have less than 2 hours to decide if you're going to get funded or not. The text quality has to be very good. And by text quality, I don't mean Queen's English. I mean, most evaluators are not native English speakers, but I'm talking about very crisp, scientific / business English. Something like you would find in an MIT review article. That's the level you need to aim for. And finally, visual impact, because as I said, the evaluators have very limited time to evaluate your application. So anything you can do to make their life easier, graphs, illustrations, that will, of course, increase your chances of capturing their attention. Keep in mind that each evaluator is probably reading 20 applications, and they're spending only a couple of hours on each. This is how the distribution looks like. A lot of proposals get stuck around 13 points with the previous scale, and they don't get anywhere because you really need above 14 to get selected to interview. Now, the Commission has changed the system. They will keep the scoring out of 15 for the collaborative, for the ESC Pathfinder, and for the transition. But for the ESC Accelerator, they're implementing a go, no-go scheme. So it really will be go or no-go, but given the amount of money they have, it's the equivalent of having more than 14. So it's the same thing. The only benefit is that it might force the evaluator to really take a position, because I've known evaluators who thought an excellent application only deserves 13 out of 15, which is of course not ideal, because at 13 you don't get selected. Now they have to make full use of the scale, because the scale is 0 or 1. In conclusion, what can you do to beat the odds? It's kind of obvious, but it's really all about good preparation and hard work. You cannot just think that you have amazing technology, you have a board with Nobel Prizes, and therefore you will, of course, deserve that funding. This doesn't work like this. You'll have to do the same amount of work than any other company filing. First of all, you need to look at the instruments. There are many of them, and depending on your level of maturity, technology maturity, commercial maturity, you might want to look at different instruments. Don't get stuck with the ESC Accelerator because your national contact point is telling you you should apply, you should apply, you should apply. These people, their job is to make sure that as many companies apply as possible. They don't really care about the success rates. So be careful. This process will take a lot of your bandwidth, even if you work with consultants. So choose the right instrument. And of course, we can ask consultants for their advice on this, and people specialized in EU funding. Commit the resources. If you want to do it yourself, you have to be ready for between 200 and 800 hours of work. There is no shortcut for this. You don't do it on a corner of a table over the weekend. That just doesn't work. If you work with consultants, you can probably cut that by 80%. So you'll end up spending 20% of that time, and the consultant 80% of the time, with a consultancy that really does the writing, not a consultancy that just looks at your case and make it pretty. Make sure to enforce deadlines. Really important, because for the collaborative projects, you need to have these steps one by one. And it's very difficult to get the feedback from all of the partners in a consortium with 30 partners, for example. So the process is very important. For the ESC Accelerator, it's also a problem, because the first step, the short step, is now on a rolling basis. So you know the problem. There's no deadline. Therefore, you can procrastinate forever. And I think this is not a good thing. So here, enforcing internal deadlines will be even more important. And finally, work with consultants, people that can provide you with that track record. We are providing this support. One thing that I want to highlight is that we work purely on success fees, as Robert was saying, which means that we succeed, we get some fee. We don't succeed, we don't get any fee. And that makes a major difference with an instrument that has a 1% success rate. We've raised about 450 million euros, but this wasn't done through sweat and tears. So it's a very difficult job for everyone, also for the companies we work with. You have to be ready for that. But if you are up for the challenge, we are happy to talk to you about this. Thank you very much, and happy to take the questions.
Thank you, Xavier. I'd like to ask you one question, because in the framework of COVID that may last for quite some time, on a very practical point of view, how will the team present their application with the EU Commission? So should they learn how to pitch in front of a computer, or will they be meeting with the jury?
So clearly, since March last year, they switched to remote conference calls for this, which is of course an additional issue. I think the only tool you need to master is WebEx, because that's the tool that the Commission uses for this. But I agree with you that it creates a completely different interaction, and I think it's worth to work on your own web presence when you do this, because there are people who are really good when they are in the room, and they can present well. Even if maybe their English is not perfect, but once they hit a webinar, then they're really struggling to make an impact. And I think this, of course, is a disadvantage compared to other people who might master English and also just a way to interact in webinars better. So definitely something to think about. In fact, in our selection process, the first thing we do is we interview you. So you pitch us. And that's one of the things we do to decide if we think you would be a good fit for the EIC Accelerator, or if you should look at other types of. For example, we might say, assembling a consortium on quantum, why don't you join this consortium rather than going for the EIC Accelerator, where maybe your pitching will not work out.
And maybe a second question regarding the EIC. You mentioned the fact that that they look at companies that already have a prototype. Yet in quantum, the definition of prototype can be tricky. So maybe for the sake of clarity for all the attendees, what could be examples of prototype? I mean, Pascal, you mentioned they had already 100 atoms, but maybe not all of them have such a development stage. So some examples of what is a TRL 5 or 6 in quantum?
So TRL is a very tricky issue, and I think that the evaluators themselves do not agree with the definitions. But the definition, the theoretical definition for TRL5 is when you have a prototype that you've tested into a controlled environment, and TRL6 is when you've been able to test it with some kind of early stage client or prospect. They could still be a controlled environment, but some external people have tested it. For quantum, I think you have to look at the stage you've reached, and if you have something you can demonstrate in the lab, you should have reached TRL5, and that's sufficient to go to the accelerator. Okay. If you haven't reached that, then you should look at the other instruments into the EIC, such as Pathfinder and Transition. Mm-hmm. A good rule of thumb is, do you have a short-term prospect that is willing to do a proof of concept with you? If so, you're probably close to TRL6, and therefore you are fit for your accelerator. If you need another 6 months or 12 months to get to that stage, then probably you're not that mature yet, but you might be in 6 to 12 months.
And there is maybe one last question. It's about so before it was the notion of EIC was for companies that could not be funded because they were too risky. Now it has changed. So on the other way, I mean, having a partner is good because it shows that you are close to TRL 5-6. But is there a problem at having too many partners, which would then qualify you as not risky enough? Or...
No, I don't think you can argue that quantum is not risky unless you are some kind of system integrator who uses existing technology building blocks. The definition has changed. I think in the previous framework, they were looking at what they call non-bankability, which was an issue because essentially they were selecting companies who couldn't raise any funding. But then once they got the funding, then they were asking them to bring co-funding. So they kind of changed the rules in the middle of the game, which was a bit confusing. Now they have made a clear statement that they want to provide equity on a 50-50 basis, meaning that if you ask for 5 million to the EIC, you should raise 5 million from your own investors or other investors that you are sourcing. So it's not about bankability anymore. It's about risk. And how do you define risk? Well, we're back to that slide I showed at the beginning about the product market risk. Have is there a risk on the product market fit and the R&D risk? And I think both are usually present in a quantum company. So I would not say that you should have as few partners as possible. That's quite the opposite. You have to demonstrate that you are building this ecosystem to reduce that risk, because everyone knows that the risk for quantum technologies is still huge. So having partners is really good. And I think one of the reasons why IQM, Pascal, and Qbox formed, because they could demonstrate that early stage ecosystem, which was already very strong.
Okay, thank you very much. I think, yeah, we will move to the next session. Thanks a lot, Xavier. It was very clear. And if you wish to ask other questions to Xavier, don't hesitate to use the Q&A. Thank you.
Okay, thank you, Robert. Thank you, Xavier. Great talk. And actually, the transition is fairly easy because I'm pretty sure that Qu&Co will be an awardee of one of the EICL Accelerator grants very soon, and hopefully with your support, Xavier. So we'll have now a presentation by Qu&Co, a company I've got to know some time ago already. Very excited to have them here today. It's one of the very first quantum software companies born in Europe. As you know now, there are some great platforms now for quantum computing, some hardware, conducting qubits with IQM, AQT on ions, Pascal with atoms. There are several photonic platforms in the Netherlands and in France with Candela as well. But we need also software, and I'm really happy that we've seen Qu&Co come and figure among the leaders in this field, because we need definitely a successful software industry born in Europe. So we let them explain about their recent developments, which are really super exciting. And one thing I'd like to mention as well, I'd like to thank Benno in particular about his involvement in the ecosystem. So I was with him in a meeting this morning. I'm not sure I'm allowed even to disclose that, but today was the day when the Quantum Industry Consortium from Europe, the QUIC, was created with it's a little bit the equivalent of the QEDC in the US for the ones among you who know the US ecosystem. So it will represent the ecosystem, the industry, towards the European Commission and other stakeholders. And Benno has been very active in making that happen. So I thank him very much for that, and for accepting also, if I'm not wrong, to be the interim vice president. So we'll have some news about that, I guess, over the next weeks. It's not official yet, but I wanted to share the news and thank him for his involvement in the community. In that sense, it's important that we all spend times, even if we have day jobs, doing this kind of thing. I think it's to the benefit of all. So with that further ado, I'll leave it to Vincent and Benno to tell us about Qu&Co and a very exciting topic, solving nonlinear differential equations with their new algorithms.
Thank you very much, Chris, and also for your kind words, and of course for inviting us to this meeting, to this talk. And hello, everybody. My name is Benno AUBRY, and my background is in experimental quantum physics. But as this happens to many people who start out in academia, I left the scientific community, and for me that point was already over 20 years ago, to pursue a career in consulting and later in the financial sector. But several years ago, I decided to come back to quantum, and together with Vincent ELFVING, I co-founded Qu&Co. But maybe Vincent, you want to say a few words about yourself?
Yeah, sure. Yeah, my background is in physics. I did my PhD in quantum information at the Niels Bohr Institute. I worked for a while at Google in Santa Barbara, working on the implementation of practical algorithms for NISQ devices, and specifically superconducting qubits. And now I'm at Qu&Co as a role of CTO.
Thanks. Yeah, just to give you a very, very brief background about our company. Qu&Co is a quantum startup. We are based in Amsterdam, and we develop quantum algorithms and software for chemistry, material science, and multiphysics simulations. So the quantum algorithms we developed, they range from algorithms for atomistic level chemistry simulations to quantum enhanced machine learning, and also to applying quantum neural networks to solve differential equations. And the latter topic is the one that we will be talking about today. But before I hand over to Vincent, I just wanted to state that the work we will be presenting today was done as part of our ongoing research collaboration with Alexander Kirienko at the University of Exeter. So we also want to thank him for all the wonderful things that we will be presenting today. So over to you, Vincent, and to the rest of you, enjoy the rest of the talk.
Sure, thanks, Benno. So I'll start with a little bit of context of what we're trying to solve, and before going more into the details of the algorithm and trying to explain what we did there. So we found that many interesting problems among our clients consisted of problems that are typically modeled by differential equations. And we can intuitively understand this because a lot of the physical systems that we encounter, we know the fundamental laws that govern these systems, right? So we know that there is some conservation of mass and transport of energy. We understand that these are effectuated by forces. And in terms of rate of change, we can describe them with differential equations. And typically, these are very challenging to solve with classical computers. And even to solve them at all, we need to make some approximations and we need to choose some sort of strategies to solve these methods. And classically, what we know of roughly to sort of categorize these methods is that we can distinguish sort of the macroscopic and the microscopic approach, where microscopically one would actually track each individual particle in your system. So that can be like cells, proteins, it can be, or even individual molecules, leading to a large number of coupled differential equations that are interacting. And typically you would use Monte Carlo type of methods to solve these. But what we'll focus on today is more the macroscopic thing. So starting from the equations of motion for larger systems, including hydrodynamics, for example. And typically the type of methods that we use to solve these in a macroscopic fashion is these global or spectral methods, or more local and grid-based methods. Where spectral is aiming to decompose solutions into, for example, Fourier series, and grid-based methods are actually treating and discretizing real space by a grid or finite elements. And to set up sort of the comparison of different types of classical and quantum solvers for these differential equations, I here sort of make this grid where we have on the left-hand side the deterministic ones, on the right-hand side variational ones, and at the top classical and the bottom quantum. I will not go through everything in detail unless you want to read everything, but the main takeaways here are that the deterministic methods lack the variational principle. That means that basically if you have a solution, that's just the solution you're going to have. And the only way to improve this systematically is by just increasing your accuracy by adding more grid points and discretizing your space further. But in recent years, notably in the classical domain, coming out of academia, being more and more applied to industry, are these neural network-based solvers for solving differential equations, which takes a radically different approach. I'll come a bit back to that, how they work, a little bit later. But in the quantum domain, most of the early solvers for differential equations have been based on the idea that quantum computers are very good at treating high-dimensional linear algebra. And intuitively, one can imagine that you could perform very high-dimensional matrix manipulation, and also the HHL algorithm is a particular subroutine that allows you to do matrix inversion very efficiently. So if you can discretize your system into a set of coupled linear differential equations, then you can apply HHL and solve your problem. But typically, this requires you to linearize your problem, and that incurs some approximation. And the other problem with those HHL algorithms is that there's this data input-output problem, because your solution is encoded in the amplitudes of a wave function, which we know is hard to actually fully apply tomography to. Furthermore, typically these derivatives are estimated using finite differencing instead of actually doing analytical derivation like we have in these neural network methods. So more recently, these variational quantum solver was proposed. I think it was in 2019, that are actually also still using this amplitude encoding, but it allows at least to do some efficient implementation on NISQ type devices by applying the variational principle. So you have relatively less deep circuits than HHL, and you can still apply a nonlinear component to it. So these solvers work, but they're not completely flexible. So we looked at those and thought maybe we can improve on that. So these neural network solvers, how do they work in the classical domain? Basically, you can observe the neural network as being some nonlinear function generator or a universal function approximator, right? So given some input x, it produces some output f of x. And the idea is that you train the neural network to represent a function that solves a differential equation given some boundary condition. And if it doesn't actually adhere to it for a given f, you variationally optimize the neural network weight until some convergence criteria and your solution satisfies your differential equation boundary condition satisfactorily. And this I just give for a simple example here, but we can also generalize this to any higher order and higher degree of nonlinearity in the differential equation. Typically, we just want to know that the left and right-hand side match, right? So recently, an interesting proposal was made in the context of quantum neural networks, in particular for application in supervised learning tasks, where this quantum circuit learning idea was made that allows you to map input, so training data, onto a quantum circuit using a quantum feature map and variationally train a variational or parametric quantum circuit until the output represents or fits or does regression on this training data upon convergence, right? And these trained functions can be highly nonlinear. And that is making use of this quantum feature map and this quantum variational circuit, but it is actually applied just for supervised learning tasks. But what we propose with DQC is that we use this structure of QCL in order to do this universal function approximation. So we produce trial functions by measuring on the output of a quantum circuit. But in addition to that, we then check whether that function adheres to the differential equation of our model that we are interested in and to the boundary condition, and then update the variational parameters as we go along. So pretty straightforward, except there's one key ingredient missing, meaning that we do not only need the function value f of x, but also its derivatives. One could approximate this by finite differencing methods, as other schemes have done before. But actually, QCL has described also a way to do circuit derivatives, meaning that we can compute analytically the derivative of f of x using circuit differentiation. So the DQC circuit consists of these two parts. We have this quantum feature map circuit and this variational quantum circuit. So let me show you how this works. So keep in mind that we represent the function as an observable measurement on some cost function c over the wave function that comes out of this circuit here. But if we differentiate the first circuit with respect to the variable x that goes in here as a component to the feature map, we actually get out a sum of feature maps with slightly different angles in the case of the parameter shift rule of circuit differentiation that we apply here. So that means that we can evaluate analytically the derivative of f of x on the quantum computer by simply evaluating or measuring this cost function over a state that's produced by a slightly different feature map depending on this parameter shift rule. And this is all programmatically or automatically. And it pretty much resembles the automatic differentiation that you know of in neural network, classical neural networks. And as an example in the paper, we show how a spectral type of feature map, in particular Chebyshev type feature map, can be used to solve particular kinds of differential equations. And the idea is that with a Chebyshev decomposition, much like Fourier series analysis, one can, with a finite number of Chebyshev polynomials, very accurately approximate solutions. So here I draw in light blue the correct solution, and with increasing number of Chebyshev polynomials, we can approximate this function quite nicely. And the theorem says that in the limit of infinity, number of basis functions, we can approximate any function. And the neat thing is that we can consider up to 2 to the n number of Chebyshev polynomials, where n is the number of qubits, depending on the type and form of particular feature map we use. In this case, we actually apply a feature map consisting of just single qubit rotations, where each rotation depends on x with some nonlinear function, this one particular. And if you choose it in this particular way, and if you do the math right, it shows that we actually project onto Chebyshev polynomials of first and second kind that also incur an additional order n that is different for each qubit. Okay, great. So then we can produce sort of like a representation within this really large Hilbert space. But then how do we actually measure this function, f of x? Well, we do this by Hamiltonian averaging in the case of the NISQ version of DQC. So we devise a cost function c, and the aim of it is just to uniquely and discriminately map the wave function that comes out of the circuit to a particular value that represents this function here. But we are free to choose this cost function. So typically one would choose something that has a sort of a rich spectrum, so many distinct eigenvalues. But in principle, you can choose one, and you can even optimize this one over the optimization trajectory. So how do we know then that this solution f of x is actually good? How do we quantify the quality of this trial solution to the differential equation? Well, we use for that a loss function. Just like in classical neural network systems, we parameterize the differential equation and treat the boundary on an equal footing inside of this loss function. And the loss function basically says, okay, so how far, if my function does not solve the differential equation exactly, then how much does it not solve it? By how much? So we can quantify this by any kind of loss function. This can be a mean squared error, absolute error, but we just say how much does left-hand side and right-hand side not match? And we evaluate that over m different training points over the domain of interest, x. So in this sense, we can treat how well does a solution conform to the differential equation. And then the differential equation can be any kind of shape or form, because all that we need to be able to do is classically post-process the data that comes out of the observable measurements. In a similar fashion, we can treat the boundary. If we know that at x0, the value should be u0, then we can always say that, okay, how far are we away from that? Let's quantify that with some loss. And we can tune the parameter in front eta to say how important it is to us that we conform to this boundary. So here I show a schematic overview of the full workflow, where on the right-hand side for your viewing pleasure is some particular example where that just shows the concept of training the solution, right? So where we initially have some randomly wobbling combination of Chebyshev polynomials, but over the course of the training here on the bottom, we get an increasingly nicer picture. And this is an image we just got in from our student, Annie Payne, so thanks for that. But the schematic overview is we have this input, differential equations and boundary condition. We have a lot of choices here. There's an active ongoing research to choose the right choices here. We have feature map, variational ansatz, cost function, loss function, and a way to choose the boundary handling. And the whole procedure is basically this variational procedure over the loss function optimization, where the loss function is computed by computing its constituents, right? And its constituents being, of course, the function itself, evaluated at all the training points x, and the differentials at every point x, evaluated by these derivative quantum circuits analytically. And furthermore, we can aid training by computing the gradients with respect to theta, which is the parameter that we optimize over in the loss optimization. And we exit the optimization upon some convergence criteria, where we see that the loss doesn't improve further, for example. And at the final theta that determines how the variational circuit is optimized, we can evaluate then on a very fine grid or in whatever area we were interested in what this solution looks like. So we applied this to a particular problem, which is the 1D Navier-Stokes kind of problem. This is all in the paper as well, where we treat this convergent divergent nozzle and we solve it with DQC. So in this case, the equations to solve is actually a set of coupled differential equations, right? And that's not any challenge here because, well, in principle, not a fundamental challenge because we can add all of the contributions as parts of the loss function again. And the problem setting here is that we have some incoming subsonic flow coming into this, going through this nozzle, and for particular boundary and initial conditions, we expect this supersonic flow to come out. And this is actually known to be a stiff problem or a difficult to treat problem, even though, of course, with the right methods, you could solve it still on a laptop because it's just a toy problem. And in this case, we used 6 qubits in our DQC solver, and we found the nice convergence. So on the right side, we have the loss functions as a function of the iterations. And we, on the left-hand side, show sort of a slice here where the optimization was not yet fully completed. But here in the middle, we show that the optimized solution very nicely follows the solution that we know from classical methods. So I hope that these steps and examples sort of show some of the benefits of using DQC, but I can kind of highlight this also further when we compare our method with deterministic and variational quantum solvers. So I showed you how this input-output problem is solved by the quantum feature map and Hamiltonian averaging step respectively. We expect that the variational aspect of it makes it suitable to noise more than HHL type of problems. Scaling is still unknown. We cannot give a big O notation scaling to it, but in our experience, it showed very nice convergence speeds. It does treat nonlinearity directly, so you don't need to do linearization. And it's very flexible. So we can allow many different kinds of differential equations in principle, although of course further research is needed to actually check whether it really works for all of these different problems. So that's an exciting ongoing thing. And as an outlook, I want to briefly mention that training these DQCs is probably one of the hardest things and the biggest challenge, just as it is with classical neural network solvers for DE. So there's a lot of tricks over the past few years that have been developed, and we hope to use these tricks also for DQC. We have so far only implemented in a wave function-based simulator, but we also want to do something with noise and with actual NISQ hardware. And we in appendix show also how a potential FTQC version would look like, assuming fault-tolerant, fully coherent execution that can perform parallel training and avoid this pricey Hamiltonian averaging. So very, very short, but please ask any questions, and thanks for your interest.
Thanks, Vincent.
Yep.
Thanks very much for the presentation. I had a couple of questions, but you actually answered some of them, but I'll come back to that. But we have 2 questions from the audience. One from Hermani on barren plateaus. I think it's a problem for quantum neural networks. That's well known. There's been some recent papers on that. And by the way, there has been a couple of very nice review papers on the archive on variational algorithms where you have features, if I'm not wrong. So you have a way to deal with barren plateaus, any specificities in your method? How do you get around that?
So I think barren plateau is actually a very big issue for a lot of variational quantum algorithms. And I'm not so sure whether we have particular specificities that make it less sensitive to this phenomenon. In terms of the training in general, we do have some tricks that we can do in order to aid sort of the convergence to the right solution. For example, we can use tricks like, what's it called? Oh, this disappeared. We can use some tricks based on regularization that's also known in the classical machine learning community. But this is, I'm not sure if this can actually solve the barren plateau. So that's an interesting question. Yeah.
Oh, okay. So another question that's a bit technical: how is the number of evaluations in the derivative scaling with the problem size?
Sorry, could you repeat them?
It's also written, how is the number of evaluations in the derivatives scaling with the problem size due to parameter shift technique? So that's a bit technical, I guess.
Yeah, so it depends on the specific feature map, right? So I don't know if I have a nice slide for this, but basically the reason that you have multiple quantum circuits to evaluate in this slide that I have here is because we have to apply the product rule, right? So if we have the feature map that has multiple rotations, then you have to apply this also to multiple gates. So you have to apply this parameter shift rule in different ways. And so short answer, it depends on your feature map. In this particular case, the number is equal to the number of qubits because we have those many single qubit rotations.
Yeah, I think there's one question, and actually you touched that a little bit. So have you tried the algorithm on some platforms, IBM Q, over hardware that are available to you, maybe IonQ or others?
Yeah, so that's what we're currently doing, but we don't have any public results on that yet.
Mm-hmm. Okay. And I think I have another question I wanted to ask you. So we've seen at the beginning of the presentation that you have and that's how we got to meet actually. So you had an interest also for more chemistry related problems.
Mm-hmm.
So you're looking also at other categories of problems, not only PD
mm-hmm.
like here. Yep. And you've published, I think it was in September, a paper that was a little bit, let's say, lukewarm on the prospects, on the perspectives for quantum computing for drug discovery, together with some folks from Schrödinger as well. So can you comment on your view also on the potential of perspectives for NISQ computing for drug discovery? The paper I found was, yeah, what it is. It's your assessment. But is there something, some bright future still for NISQ in the NISQ era for chemistry, particularly in drug discovery?
Yeah, great question. So indeed, I wouldn't use the word lukewarm per se, but I do think I understand the sentiment. I think that there is still a lot of potential of NISQ in chemistry. It's on the comments that we made in the paper refer rather to the particular direction that we've seen so far, right? Of applying NISQ quantum circuits following exactly UCCSD applied to some basis sets for small molecules. The particularities of the directions that we're seeing are the problem rather than NISQ by itself. So I do think that there are a lot of opportunities left for researching in chemistry and in general, right? So that's also something we're still pursuing. And yeah.
Yeah, okay. No, very, very interesting. I think it's important to realize what these machines are good for, and I think you're going to the right direction. So it's very good. So no further question. I think I'd like to thank you very much for your presentation. Very clear and very good. I really look forward to see implementation of hardware and what you will publish out of it. I think a lot of people in the community is looking at that. I think the field is super interesting. I think if you crack the code in a way, I think sky's the limit in many ways. I mean, Navier-Stokes, computational fluid dynamics. I mean, this is really huge. And it's super interesting. So thank you, Vincent and Benno. Thanks, Xavier, for being with us today as well, and Robert. We'll see you very soon in a new webinar in a couple of months. And in the meanwhile, have a great rest of the day. Thank you very much.